So welcome everyone to the seminar. Today it's my pleasure to introduce Yoni Kahn, who's joining us virtually from University of Illinois. So many people will know Yoni, and Yoni's worked on quite a broad range of topics and done some really interesting work, particularly recently on dark matter, and kind of coming up with very novel and interesting new searches for dark matter that explore a range of different kind of technological capabilities in different fields, and particularly in the context of axions, which is what he's going to talk to us today about. A new way of detecting the axion using superfluid helium-3. So thanks, Yoni, for taking the time to be with us, and I'll leave it in your hands.
Thanks a lot. Well, it's nice to be presenting remotely. As I told Kieran, I'd love to make it down to Australia before too long, but thanks for giving the opportunity to do this remote seminar. So this is work done with two postdocs at UIUC, Christina Gao and Jan Schut-Engel, and then a really amazing undergrad, Ara Monday, who started working with me, and then three superfluid helium experimentalists at Northwestern, one of whom amusingly was the one who taught me undergraduate quantum mechanics. So it was really fun to start collaborating with one of the people who was my teachers now and get to teach him a little bit about axions, and then also Josh Foster, who's a popularity fellow at MIT. The outline is as follows. So I'm going to remind you all what the axion-Wind is. Given the population of this group, I expect that a large number of you might have already heard about this. So this will be some review using the really nice plots that Kieran has put together. And then I'll give you a crash course on both nuclear magnetic resonance and superfluid helium-3, because the novelty of the system I'm going to describe has to do with some really interesting condensed matter physics that was discovered back in the 80s and 90s that we kind of figured out how to turn into a detection modality for axions. In particular, there's a funny thing that happens in superfluid helium-3 and basically no other system that I'm aware of, called the homogeneous precession domain, that I'll explain the theory of. It's kind of like a nice mix of stat mech, condensed matter physics, and high energy physics, and then how we finally use that to look for an axion signal and what kind of sensitivity that we can expect. Okay, so I'm sure many of you have seen this plot before. Dark matter exists. We don't know what its mass is. I'm going to focus on this talk on wave-like dark matter, so something lighter than about an eV. Its number density is very large, but the kinetic energy carried by any individual particle is very small. So this thing behaves like a classical field that is just pushing on basically any quantum mechanical system you can imagine. So here's a schematic of the abracadabra axion experiment that I've worked on. This is ADMX. This is what happens if you have a light particle that talks to photons, but it can talk to lots of other things as well. And those are the kinds of couplings that I'm going to focus on. Okay, so just to remind you how wave-like dark matter behaves today. So it's a field whose amplitude is set by the local dark matter density. It oscillates at a frequency set by the dark matter mass. And it has spatial variations, which are suppressed compared to the temporal variations by the velocity dispersion, which is on the order of the mean velocity, which is about 10⁻³ times the speed of light. The fact that the dispersion is small means that you have spatial and temporal coherence. And so the Compton wavelength of this field is about a factor of 1,000 smaller than the de Broglie wavelength, which is roughly about how far you have to go before the field gets out of phase with itself. And you get an extra factor of V. So the coherence time, the number of cycles this field can oscillate before it goes out of phase with itself in time, is about 10 to the 6 times the Compton time, or just the inverse of MA. And then if your mass is 10⁻⁹ eV, your number of quanta in the field is extremely large, per unit volume. And so thinking of this as a classical field where the difference between n and n+1 quanta is negligible is totally fine. Okay, so given that, what can such a field do to standard model particles? And so I'm going to, be focusing in this talk on, motivated by the QCD axion. If your ultralight particle is the QCD axion, there's only one parameter in the problem, which is the Peccei-Quinn symmetry breaking scale FA, which is inversely proportional to the axion mass. And then all the coupling to all the standard model things that you can write down all goes like 1/FA. So the coupling to photons, the coupling to nuclear spins, or the thing that might solve your absence of a static neutron EDM, those couplings are all proportional to that same parameter. But let's think broadly. So we can imagine axion-like particles that have two independent parameters: the mass of the ultralight field and the typical size of its coupling. So given that, what can we measure? So the universe is suffused with this oscillating field that is dark matter. And so if you put in a static something, what you get back, given the interaction with the axion, is some oscillating something else. So the example many people are probably most familiar with is if the axion couples to photons, you stick in a static magnetic field, and then the interaction with the axion, this time derivative is non-zero, so you get back an oscillating response field, an oscillating electric or magnetic field. Likewise, if your axion couples to nuclear spins, that means you get an oscillating effective magnetic field, because you look at this Hamiltonian, this looks for all intents and purposes just like what you would write down for B dot sigma, the Hamiltonian for a spin interacting with a magnetic field. And this thing, this grad A, picks up the time dependence of the oscillating axion, but also picks up a factor of the velocity from the spatial gradient. And then also, if your axion solves the strong CP problem, it couples to the neutron EDM. And so you get, on average, 0 static neutron EDM, but your neutron EDM in an axion background will oscillate, again, at a time scale given by the axion mass with an amplitude proportional to the field amplitude. Okay, so I'm going to focus on this operator that's circled here. This thing is called the axion-Wind, since the gradient brings down a factor of the velocity. So the direction that this gradient points in is the average velocity of the dark matter field. Okay, and I should say, please feel free to interrupt as we go. I have the video panel here, and I can see the chat. So if people want to stop and ask questions, please feel free as I'm going. Okay, so here's where I come to the very nice plots that Kieran has put together. So here's the landscape of axion detection as it stands today. So these are all existing limits. So on the left is the photon coupling, and on the right is the neutron spin coupling. And so you can just see by eye, there's tons more experiments that are looking for the photon coupling because it's easier to look for. There's lots of ways that you can interact with electromagnetic radiation at various different frequencies, from laboratory constraints to cosmological constraints to astrophysical constraints. But there's a heck of a lot more white space on the plot on the right, this coupling to neutron spins. And really, only recently, within the last like 6 months, do we have any experiment that can dip below the astrophysical bounds that we got back in 1987 from just emission of axions during a supernova. So I think there's a lot more room for ideas and experiments in the other axion coupling space. Note that I haven't put here the projected experiments, not because I want to give short shrift to any of the really good ideas, but just to say that, the real test is like, if you have an idea, let's go and take some data and see what happens. And that's what these co-magnetometer experiments have done. Actually, this one, the one that has the strongest limit, is once again analyzing old data that already exists. So you can get a lot of mileage out of just cleverly interpreting data that's already been taken in another context. But we are quite far away from the interesting parameter space kind of given by these shaded brown lines here. Okay, so just focusing now on the this coupling to nuclear spins. So this effective magnetic field sourced by the axion, you're dividing by the gyromagnetic ratio because the Hamiltonian is actually just gamma times b. So you just multiply and divide by gamma. So that means the effective magnetic field felt by a given nucleus is going to depend on the gyromagnetic ratio of that nucleus. So here's a number that happens to be 0.69 inverse GeV for helium-3. It's roughly 1 over the mass of the nucleus. And then this thing oscillates at a frequency given by the axion mass and points in the direction of the velocity. If you plug in numbers, you think, okay, this is an effective magnetic field. So let me just use a magnetometer and figure out, can I just detect this thing? If you're on the QCD line, this is a very, very small field. So for a mass of 10 to the minus 7 EV, this is a field of about 10 to the minus 23 Tesla. We don't have magnetometers that are quite that good. At least sort of a generic magnetometer that's not tailored to a certain task or frequency range. However, this field has a coherence time at this mass of about 40 milliseconds. And so what you really want is you want to exploit the long coherence time to achieve some sort of resonance to boost your signal to try to turn this very, very small field into something that's detectable. So the traditional way this is done was pioneered by the CASPEr experiment that goes back to some papers by Peter Graham, Sajid Rajendran, and Dima Booker back about 10 years ago. And the idea is the best sensitivity for magnetic fields typically comes from nuclear magnetic resonance experiments. So if you have some sample of spins and you put a magnetic field, say, along the z direction, and the value of that magnetic field is tuned to the Larmor resonance of the frequency of your external magnetic field, whether it be a real magnetic field or an effective one like the one sourced by the axion. If you satisfy this resonance condition that gamma times your static external field is equal to the frequency of your oscillating B field, the average spins will tip away from the vertical by some angle delta beta. And that angle grows linearly with time up to the minimum of either the coherence time of your oscillating field or what's known as these transverse spin coherence time or transverse spin relaxation time, which is the time it takes for the spins in this medium to go out of phase with each other and damp out your signal. And so your signal so you're looking for a transverse magnetization. So in other words, a magnetic field that points in the perpendicular direction to your large external field. If you Fourier transform the signal, you see this nice Lorentzian peak, which sits right at the central frequency and has a width given by this T2. So what I'm going to describe for you is this somewhat exotic system of superfluid helium-3 that can get around three practical issues with this CASPEr setup. And so the first one is that doing a small amplitude detection is noisy. If you go back and look at this plot, so you're trying to detect a very, very, very small transverse magnetization proportional to that tiny effective magnetic field. And so you're going to be competing with whatever the baseline noise is on the power spectrum of this transverse magnetization. And so if you're using like a squid for readout, then you care about the flux noise through the squid. And there is some limit for that that's given by just the standard quantum limit that's pretty hard to get below. So I'm going to describe a way to turn an amplitude into a frequency. And that's great because we have really, 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 really precise frequency standards, which are given by atomic clocks. And there you can get the noise much, much lower, sort of compared to the baseline amplitude flux noise you would get from some sort of standard squid readout. So the second advantage of this system is that if you want to look for a daily modulation signal, which is really a smoking gun for dark matter, the direction of the axion wind is going to shift over the course of a day as the Earth rotates. If you're scanning through Larmor resonance frequencies and you want to see the daily modulation, you have to go back and scan the same frequency again at some other time during the day to see the modulation of the signal. The system I'm going to describe for you naturally scans through frequencies all by itself. So you basically set it and forget it. You run the experiment multiple times during a day, and you're naturally measuring the same frequencies over and over again. But every run of this experiment can naturally cover many different possible axion masses. So you don't have to go back and rescan to see a daily modulation signal. And then the third thing, might seem like it's really just kind of a practical, nitpicky kind of concern. But from my understanding, this is actually a considerable limiting factor in the actual CASPEr experiment, which is that T2 is a theoretical spin relaxation time. But what actually matters is T2 star, which is what T2 really is in your experimental setup. So if your external B field is not perfectly homogeneous, every part of your sample is going to see a different Larmor resonance, and they're going to go out of phase with one another faster than you would if your field was perfectly homogeneous. And getting a perfectly homogeneous field is quite tricky. And so in any NMR setup, you look at this gray curve, and that's what you think your relaxation time constant should be, but actually the curve damps out faster. However, in the system I'm going to describe, the B field gradient, so the variation of your large external field, is a feature rather than a bug. The change in that magnetic field is actually what gives you the broadband sensitivity. And so not only are you insensitive to having some variations in your B field, you can make it as large as you want in order to scan over as many different axion masses as you want to. Okay, so with that setup out of the way, let me just give a lightning review of the key features of superfluid helium-3. So helium comes in two forms, helium-3 and helium-4. Helium-4 is a boson, helium-3 is a fermion. They're both superfluids, but for different reasons. Helium-4, you can just have a Bose condensate of bosons by itself, but helium-3 have to form up into Cooper pairs, which are then bosons and that can Bose condense. But unlike in conventional superconductors, you have a non-zero angular momentum for these Cooper pairs. So this is known as a P-wave superfluid, and that leads to some interesting structure in the phase diagrams. There's two phases called the A phase and the B phase that just are questions about which spin states occur with what probability. In what follows, I'm only going to care about the B phase. And so I'm kind of neglecting a lot of really interesting condensed matter physics, but the thing to note is how low in temperature you have to go to actually see this phase. So you have to be below a millikelvin or at pretty large pressures in order to access this phase. That makes it kind of tricky to set up a superfluid helium lab. This is apparently very popular back in the 80s and 90s and kind of fell out of favor. There aren't a lot of labs that actually have the capabilities to go down to these ultra low temperatures. But luckily, one of them is just up the road at Northwestern, about 3 hours away from Champaign-Urbana. where my collaborators are. And then just one other number is that the magnetic susceptibility, so what is the in medium field that you get given a B field that you put in from the outside, that's about 10 to the minus 7. Ideally, you'd like that number larger because that's going to control the strength of your signal, but that's just a God-given number, and that's what we have to work with. So that's what that number is for this particular system. Okay, so let me just show you this really nice animation that's better than anything that I could have made to show you how NMR works in an ordinary non-superfluid helium-3 system. Let me make sure the sound is off on this video. So what you're seeing here is some semi-classical picture of the oscillation of spins in the presence of some external B field. If you do an NMR experiment, like if you get an MRI or something, what you do is your body is put in a magnet, and then you send in a transverse B field. You send in some pulse that tips the spins away from the vertical. So the duration of that pulse basically tells you the angle at which those spins are supposed to tip, and then they relax back to the vertical with an envelope determined by that transverse spin relaxation time. So what frequency are these spins precessing at? They're precessing at gamma B naught. That's the Larmor frequency. And you need to put in a certain duration of your transverse B field in order to get the spins to tip at some large angle. And then this FID, or free induction decay curve here, is just the trace of the transverse magnetization as a time series. Okay, so the dynamics of these spins are just governed by the Bloch equations, which are just the semi-classical equations for just, torque is m cross b. And so, oops, I think this should be an equal sign, not a minus sign. So you can split up the magnetization into transverse and longitudinal components, each of which have their own relaxation times. Typically, the shorter one is what dominates, so the longitudinal relaxation time is much larger than the transverse one. Okay, so that's what happens in kind of a vanilla system like the one that CASPEr might use. They might use hyperpolarized xenon. A funny thing happens in superfluid helium-3 in the B phase. So let me imagine that I have my superfluid helium. I got some cell. I put in my external magnetic field in the z direction, and let me be especially perverse and let me make sure that that thing has a gradient. So the B field actually varies over the size of the sample. So everybody here is going to see their own Larmor frequency. And let me apply a transverse magnetic field of any amplitude and duration whatsoever. So generically, what that's going to do is just randomly orient all the spins. Some are going to tip more than others. They're all going to be precessing at their own frequency. If I wait 20 milliseconds, the following happens. The system spontaneously self-organizes into two domains, one of which is all tipped at the same angle and all precessing at the same frequency, despite the fact that the magnetic field is varying over this domain. What frequency is it precessing at? It's the frequency corresponding to the local Larmor frequency at the position of this domain wall. Oops. And then the second domain down here at the bottom, there's no precession. It's completely relaxed. It's as if there wasn't any, it's as if you never put in the transverse field in the first place. This tip angle is inverse cosine of -1/4, which is known as the Leggett angle. And that has to do with the strength of dipole-dipole interactions. And that comes from the really sophisticated condensed matter physics that governs the quantum mechanics of the system. Okay. So this is what's known as the homogeneous precession domain, and is this very peculiar phenomenon that, to my knowledge, is only exists in this particular system of superfluid helium-3b. Let me just pause here and see if there are any questions on anything that I've covered so far.
I mean, I have a general question, which I don't understand that at all. I mean, what is causing this? You're going to explain. I mean, but
yeah. So
to me, that's all.
Right. So what I can tell you is that I can reproduce the phenomenology of this semi-classically using the Bloch equations, but I need one piece of input from condensed matter physics, which is that something in the system is locking the transverse and longitudinal magnetizations together at this angle. And that is spin supercurrents. So there are very fast spin supercurrents that rapidly redistribute angular momentum among the system. And so the picture of individual spins is actually the wrong one. This is all in the same quantum state. There's no sense in which, like, there's this spin and this spin. It's just a quantum state with a certain magnetization. This is a really nice review, and these two reviews are sort of the most understandable for me as a particle physicist as to what's going on. I can give you a couple stat-mechy type explanations as we go. Yeah, it's super weird, and this is kind of discovered as a curiosity back in the 90s, and people kind of didn't know what to do with it.
So this was sort of just observed and then understood afterwards. They just sort of saw this happening in some experiment.
Right. What you would do is you just take superfluid helium, and that was kind of back in the golden days. So I'm fortunate to have Tony Leggett as one of my colleagues. He got the Nobel Prize for explaining the theory of the superfluidity of helium-3. It was just such a weird system. You kind of poked it in lots of different ways. Like, let me just take this sample, let me just hit it with a pulse and see what happens. And what you saw is just this absolutely bonkers, enormous amplitude of this free induction decay. And so this picture is the result of trying to come up with a theoretical model for just the observation that you can just hit this thing with any pulse and it'll just ring like crazy.
So is there something special about this 20 milliseconds?
Oh, no. So I'm not sure where this number comes from. This is just the time it takes to organize into this, more kind of quasi-steady state. It probably has to do with the spin supercurrent velocity, depending on the size of the container. But I can't remember exactly where that number comes from.
So it'll depend on how big this thing is, like how
probably. But my colleagues tell me you can't ever really get more than 1,000 cc's of superfluid helium-3. It's just not possible.
Yeah, okay.
So it's never going to be that big.
Yeah. Cool.
Okay, so here's one way of understanding what's going on. So your superfluid helium-3 is a Bose condensate. When I put in a magnetic field pulse, I am pumping in units of angular momentum because I'm torquing the spins. So let me figure out how much angular momentum I put in and count that up in units of h-bar. So I can call each one of those units of h-bar a magnon. Magnons are bosons. And so what the system is doing is it's forming another BEC on top of my first BEC. It's forming a Bose-Einstein condensate of these quanta of angular momentum, these magnons. And so how do I figure out where the domain wall goes? Well, the theory of Bose-Einstein condensates tells me that I can figure out what the density is of the ground state. And then the volume of this homogeneously precessing domain is determined by the number of magnons that I pump in. So to find the volume, I just divide the number of angular momentum units I pumped in by the density of this thing. And then the system will just set itself up to put the domain wall at a location so as to satisfy this condition. So this is kind of the easiest way to understand what's going on, though it doesn't tell you where this angle beta naught comes from. So maybe one step further down the condensed matter road is having a system at constant magnon number is like being in a canonical ensemble at fixed particle number. So in the canonical ensemble, if you fix the particle number, the chemical potential is spontaneously determined. And so here's a plot of the free energy. So F minus chemical potential times density. And minimizing that thing tells me that I want to be in a situation where I have a domain wall. Either I have a minimum for this thing or I don't. And not having a minimum corresponds to this relaxed domain, and having a minimum corresponds to being in this homogeneously precessing domain. And where this free energy curve comes from, again, that comes from the microphysics of the superfluid helium-3. That's kind of where all the really heavy condensed matter physics comes in. But maybe making one more analogy, an atomic BEC, a BEC that the atomic physicists might make in a lab, is you can think of it as being an eigenstate of the annihilation operator. And what does that thing do? Well, again, thinking of this kind of stat-mech interpretation, that operator has an exponential e to the I mu t. So a spin BEC, right, where now the operator is annihilating down spins because the magnons are sort of pointing it in the opposite direction for my external B field. The spin operator is going to oscillate at e to the I omega t. And just looking at these things, I'm very tempted, and in fact, this is the correct thing to do, to identify the chemical potential with the precession frequency, right? And that tells me why this thing is all precessing at a frequency corresponding to the local Larmor frequency, which is the chemical potential of where the domain wall sits. Okay, so again, I refer you to these really, really excellent reviews if you're curious about the system. There's a lot of really beautiful physics in superfluid helium-3. But for now, I'm just going to take this as given, and we're going to figure out how to turn the crank and use this to do axion detection. Okay, so first let me tell you a little bit about the dynamics of this phase. So you're always going to have some losses in your system. atoms are going to bump into the walls, so you're going to lose units of angular momentum to the environment. And so you can only ever decrease your Magnon number. If that happens sufficiently slowly, this will reestablish local thermodynamic equilibrium adiabatically. Your volume of your HPD will shrink because the Magnon number is shrinking. But that means that the domain wall is moving, which means that you're changing the local Larmor frequency, which means that your precession frequency is drifting. So if I read out this system with a magnetometer, like maybe a squid or even just an ordinary pickup loop, and I have some frequency reference, this is the amplitude of, or this is the envelope of the NMR signal that I see. So this funny business happening here, that's the establishing of the HPD. And then after it, you see this really, really nice, damp sinusoid that, if, with this resolution, you can't really see what's going on. It's clear that the amplitude is decaying exponentially. The time scale is actually T1, which is the longitudinal spin relaxation time, which is longer typically than this the transverse relaxation time in most systems. And then if you Fourier transform this thing, you can see that the frequency is drifting, from larger values to smaller values over the course of the evolution of the system. And because your tip angle is order 1, right? You're not tipping these spins a tiny bit. Cosine of 104 degrees is pretty large. And so that means that your transverse magnetization is large enough that you can read it out with an ordinary pickup loop. You don't even need a superconductor. Just like a copper wire at low enough temperatures will be perfectly fine. And by the way, so why is the frequency always going down and not up? So in this case, the gradient of the B field establishes a preferred direction for you. It says that the HPD is always going to form such that relaxation happens going up. It's just like having a BEC and a gravitational field. Things will collect at the bottom and not at the top. Okay, so now let me quantitatively show you how you can understand those features of this HPD using just the block equations. So this is just semi-classical analysis. The only quantum mechanics I'm going to put in is the relationship between mx, my, and mz, given by the fact that these things are sitting at this magic angle. Okay, so let me parameterize the volume of this HPD by some fraction f, which goes between 0 and 1. 1 is the whole sample, and 0 is the domain wall sitting at the top, times the volume. And then I'm going to put in the ansatz that the only thing that's evolving here is the fraction of the sample that the HPD is occupying. So actually, my equilibrium magnetization already involves a factor of this HPD fraction, because it's as if the bottom thing here never really saw the precession that's happening up there. So let me put the position of the domain wall such that when f is 1, z is at minus h, and when f is 0, z is at 0 up at the top. And then I can parameterize my longitudinal and transverse magnetizations by an amplitude and a rotating phase that tells me theta dot is going to tell me the frequency at which this thing is precessing. So I'm using the fact that I know that mxy over mz is tan beta naught. So this is just the one input from the condensed matter physics, which tells you that I have to give these things the same amplitude up to these trigonometric factors. And now everything else is just going to follow. And also, that tells me that because the spins are locked together, there's actually not two separate timescales in the system. There's only one relaxation timescale that I'll call T1. Because if there were separate transverse and longitudinal relaxations, these things wouldn't stay at the same angle. Okay, I'm going to put in a convenient factor here, which is just given by the doing the trigonometry on this inverse cosine of minus a quarters. That tells me that the thing that should go here is actually 5 times what I previously called T1. And doing that and solving the equation for mz tells me that the HPD fraction decays exponentially on timescale T1. Okay, so that reproduces the phenomenology of seeing this amplitude decay. And T1 is basically now just a fudge factor that tells me, all the different sources of loss that are coming into my system. I can try to predict some of that for microphysics, but you could also just treat it as an empirical parameter that just comes from the amplitude of this decay. So how does the transverse magnetization evolve? So if I now solve this equation using my solution for f from the solution for mz, that tells me that theta dot is gamma b naught. So the precession frequency is the Larmor frequency, as I would expect from an ordinary NMR type setup. The subtlety is that secretly B is a function of position, which is itself a function of F. So these equations are coupled in an interesting way because actually theta dot is gamma B naught of Z. So it's Larmor precession at the local Larmor frequency. Okay, so now if I'm a little bit more quantitative about it, let me parameterize the gradient of my B field by saying that it's 1 plus alpha times Z. So alpha is the fractional B field gradient. If I wait for some time much less than T1, let me just Taylor expand this exponential and say that the position of the domain wall is where it started plus some velocity times T. And then in this parameterization, that velocity is just the position where I started divided by T1. Then if I plug that into my equation for theta dot, that's what I pick up for my shift in the magnetic field. And that tells me that I not only have a non-zero theta dot, I have a non-zero theta double dot, or omega dot, which is the linear change in the frequency. And that is telling me that the frequency is drifting linearly for short times with the slope given by these parameters. So controlled by the B field gradient and also the relaxation time. And so you can just see, this curve, obviously, any smooth function on short enough timescales is going to be linear. But the point is that I can understand what the slope of this thing is just by understanding the variation in my magnetic field and the amplitude of the envelope from the amplitude curve. Okay. So that was all just what is the system doing without any beyond the standard model physics. So now in the remainder of the talk, I'm going to tell you how we can leverage this to look for axions. And the logic is as follows. So let me create this homogeneously precessing domain by putting in a real magnetic field pulse. Like literally I have some coil in the lab and I put some current through it and I make a magnetic field. So I set up this HPD. And it's now going to evolve sweeping through precession frequencies. However, if there is an axion-wind, that means that will act as a weak source or sink for magnons. It will either pump angular momentum in or pull it out, depending on the instantaneous phase of that field. And that will be most efficient when the local Larmor frequency equals the axion mass. So when this domain wall scans past whatever my axion mass is, that means that the domain wall is going to change position linearly up to the coherence time. But the domain wall changing position means that the precession frequency is also changing. So that means that I get a linear drift I get a linearly growing shift in the precession frequency away from the value that it would have been had I not had an axion. And now, this is why this is a broadband setup. I can choose my B field gradient alpha, for example, to scan one axion line width of frequency in one coherence time. So there's kind of a funny mixing of time domain and frequency domain things happening here. The domain wall is moving in the time domain, but its position in the time domain tells me the frequency of precession in the frequency domain. So numerically, it turns out if you can get a T1 of about 1,000 seconds, which my collaborators told me has not yet been achieved, but is reasonable given what we've already seen about the system, then you would want a fractional gradient of about 0.02. And that tells you that you get to scan basically the Q factor of the axion times that number. So 10 to the 4 different axion masses in one sweep through the system. So if I set this thing up and wait 1,000 seconds, I can scan 10 to the 4th axion masses. And then I can just do that experiment again and again at different times of day in order to see my daily modulation. Okay, so just to put in some formulas, if I assume just for simplicity that the axion-wind is purely in the transverse direction, so the xy direction, I can put my axion field back into the block equations. It's small, so I can decouple these equations by perturbing in the small shift in the HPD fraction proportional to the small axion coupling. And then if I pretend that the axion is monochromatic, so it has 0 frequency spread, infinite coherence time, then the shift in the domain wall is going to be linear as expected, depending on the instantaneous phase of the axion when this resonance crossing happens, with an amplitude proportional to the effective magnetic field as expected. So your signal is still small, but it's small in the frequency domain. You're seeing a small frequency shift rather than a small amplitude shift. The HPD amplitude is enormous, but the frequency at which that thing is precessing is very slightly different from what you would have expected if there were no axion. Okay, so just to show you some plots, so we simulated the signal in kind of a very simple way just to start, and we're trying to do more sophisticated simulations now. A perfectly monochromatic axion field with infinite coherence time will show you this linearly growing frequency or HPD fraction, and then a linear bump away from your linearly drifting frequency. And depending on the instantaneous phase, that can either go up or down. So why doesn't this thing keep growing forever if the coherence time is infinite? Well, I can put in whatever gradient I want, and after long enough drift away, you will no longer be on resonance with this monochromatic field anymore. And so it's not efficiently growing. And so that's why this offset kind of persists through the entire evolution of the system. And just to check that things don't change too much when you put in some cartoon of the axion field. So imagining the axion field is just a scalar rather than a vector. So the axion-Wind is a scalar rather than a vector. So just always pointing in one direction, but with a speed distribution given by the dark matter velocity distribution. You sum up a bunch of plane waves with random phases, and indeed you see the same rough amplitude and the same rough behavior that you do for the monochromatic one, which means that our estimates of the signal given this monochromatic axion field, they're not going to be too far off. The effect here is greatly exaggerated for visibility. The true size of the frequency shift for an axion coupling, which is at the current supernova bounds, and fractional B field gradient, as I told you, and a mass of 10 to the -7 eV is about 10 to the -13, which again sounds like a scarily small number, but compared to the frequency precision of atomic clocks, it's actually not so bad. What's scary is the expected size of the frequency shift for a coupling corresponding to the QCD axion. In that case, the 10 to the -17 actually is a pretty small number, approaching the sensitivity of the best atomic clocks. However, the problem here is really not the sensitivity of your readout, but it's the intrinsic noise in the system, which is interesting and not the typical noise sources that you see in other axion-Wind setups. So let me first tell you what you don't have to worry about. You're at 1 millikelvin, so you just do not have to worry about thermal noise. So the only kind of thermal noise comes from the occupancy of states above the ground state of this BEC, and it's just exponentially suppressed. And so for a reasonable volume, you just don't have any of that. You also don't have any of the typical spin noise that you would have in a classical NMR type setup, because your system is just sitting in one quantum state and it maintains that coherence during the evolution of the HPD. And so you don't have any fluctuations in the quantum fluctuations in the spin states of these guys, because really this picture is kind of not really right. It's not like you have individual spins, you just have one quantum state that's all precessing. The place the noise comes from is that you have to gain or lose magnons in units of h-bar. So when I said that you lose a certain number of magnons, really this is a Poisson process. That's the average number of magnons that you lose over some time scale, but there's Poisson fluctuations in that. And so the variance in that goes like square root of the number of magnons that you lose. So here is where you're helped by having a large sample. You can still beat down Poisson noise like 1 over square root of n. So you really are benefiting from quantum coherence of the whole system. But if you estimate what is the noise that comes from the uncertainty in the domain wall position, given the stochastic magnon fluctuations, it's actually about 2 orders of magnitude larger than what you would want to see the QCD axion. So you're kind of your limit here is irreducible, just quantized noise that you can beat by trying to get a bigger volume. But really, again, it's unrealistic to imagine a volume much larger than 100 cubic cc's or cubic centimeters. You could try to increase the coherence time, but again, 1,000 seconds is already kind of pushing it given what we already know. You can tune down alpha Z naught, but that's not going to help you because it's proportional to the same thing your signal is. So right now in this setup, looks like you can't quite get down to the QCD axion, but by the end of the talk, I'll tell you why we actually think now that this estimate might be a little bit too pessimistic. Okay, so here is our projected sensitivity from our published PRL. Why am I talking, by the way, about a mass of 10 to the -7 eV? It's because we've seen that your signal grows with your axion mass. So the larger the axion mass, the signal to noise ratio actually grows with the axion mass. So it looks the opposite here. But when you divide by the noise, it actually grows with your larger the axion mass, the better you do. The problem is that this phase just does not exist for magnetic fields larger than about 0.55 Tesla that corresponds to a mass a little bit less than 10 to the -7 eV. So this is just a God-given fact, and there's nothing we can do about it. If you want to use helium-3, that's the largest axion mass you can look for. But then you can imagine taking some different parameters. The coherence times that have been observed for this particular phase are right now on the order of 1 to 10 seconds. 10 cc's is a reasonable volume that you can make in the lab right now. You can set up your B field gradient to what you want. If you integrate for 10 minutes, you can already beat in a very narrow frequency range the best limits that come from neutron star cooling and SN 1987A. We're comparing here to CASPER-Wind, but this was the published limits from CASPER back in 2017, which are possibly too pessimistic. And here I reference you the paper from Nick Rod et al. Showing that actually you can benefit from a long T2 in the CASPER system. So this curve might actually go down. As I'll mention in a second, we actually have a similar situation in our setup. And then here, what we're imagining is if you take data for a long time, like 1.5 years. So in the blue curve, this sawtooth just comes from saying, let me sit on a certain tune of my B field. Let me sit again for a month, sit again for a month, sit again for a month. You win incoherently by just doing your experiment again and again. There's no daily modulation statistics included here at all. So we almost certainly can do better than this. But we see we already have some nice sensitivity to uncharted parameter space here. And the best thing you can do is try to improve T1. So my colleagues have convinced me there is no fundamental limit on T1. It's just kind of how clean can you get your sample container. There are modes in helium-3, not this particular one, that have been observed to have coherence times of 1,000 seconds. So that's why this kind of a stretch goal, not totally unreasonable. Who knows how far we can push it, but that will also help you push toward the QCD axion line. Okay, so what we're doing now, and this is collaborations now with the other authors listed here, some undergrad Arav Monday and also Josh Foster at MIT, is adopting the time domain formalism from this nice paper by Mariangela Santi, showing the statistics that you want to do a likelihood analysis for experiments involving the axion gradient. And in particular, your signal really is a 2-point correlation function of your signal at time Tn and your signal at time Tm. And what I have not accounted for in the previous plot is the fact that your offset is persistent over the life of the HPD. You don't just get to measure that offset once, you get to measure it again and again and again and again, as many times as you can measure the frequency of the precession. And so roughly speaking, you get kind of for free a boost in your signal to noise by square root of T1 over the axion coherence time, which is pretty large because if axion coherence time is 40 milliseconds and T1 is 1,000 seconds, that's a pretty large number. And again, your signal is not growing. You just get to measure it again and again as the noise is just fluctuating randomly above and below the expected frequency drift. So we're working on trying to actually put this into a real likelihood analysis to try to figure out how to take advantage of the daily modulation. But just to give you a very, very, very preliminary projection, that black line for 10 minutes of integration time turns into 10 seconds. So if this is right, and again, this remains to be checked carefully before we put this out, you can basically turn on the experiment and already beat the best astrophysical limits, again, in a very narrow frequency range. But the really exciting thing is now we think you can actually get QCD sensitivity if you tune your gradient to be very small, so you're sitting at a very narrow range of frequencies. You're sitting there for a long time. We think you can actually drill down and eventually beat that stochastic noise just by measuring again and again to get some QCD axion sensitivity here, where, to my knowledge, there aren't really any other experiments that can, except for Nick Rod's updated bounds from the CASPER-Wind experiment, which look like they might get some sensitivity also in about the same mass range. Okay, and then the very last thing, and this is just kind of fun, is can we set a limit now? So this is the data that I showed you from the HPD that was taken back in the 90s. No one was looking for axions then. No one made any effort to optimize the setup whatsoever. But look, you've got a frequency shift. You got some coherent or some T1, which is probably about half a second. And you can look at this thing and say, hey, look, what if I want that bump to be smaller than the width of these pixels in this digitized plot? Roughly speaking, that corresponds to an axion coupling of 1 inverse GeV, which is really, really large and deeply ruled out. However, the best existing bounds from CASPER-Wind are at about that level of coupling. In, of course, a different mass range, they're looking at about here, so 100 nanoeV, so 10 to the minus 7 EV, whereas here, the frequency they were looking at was corresponding to about 10 to the minus 9 EV. But one thing we want to do with our statistical framework in this upcoming paper is just to do the analysis on this data and then say, look, that data is 30 years old, so we can almost certainly do better now. Okay, so let me just wrap up, and then I'm happy to, I think we have plenty of time for questions. So the 3 advantages that I claimed of the superfluid helium system are as follows. So we turn this small amplitude, this Fourier transform, this power spectrum of your tip angle into a small frequency shift, which let us leverage using precision frequency readout, things like atomic clocks as frequency standards. Note that I'd never incorporated those into the noise floor because the best atomic clocks, actually, you can buy an atomic clock off the shelf that has a fractional frequency precision about 10 to the minus 13 or 10 minus 14, which for the couplings we were looking for the short kind of timescale experiments are already, that's already well below the stochastic noise floor. You get the broadband sensitivity because the HPD naturally scans frequencies, and then this phase is robust to changes in the B field, and you have very long spin coherence time. So again, from this really nice review, the thing that really made people excited about this phase is that it lives many, many times longer than the dephasing time that would naively be caused by the inhomogeneous B field. So there's a really nice active collaboration with low temperature experimentalists at Northwestern, and also people that do atomic clocks and frequency standards for a living at UIUC. And hopefully we can try to take some preliminary data soon in this 10 to minus 7 EV and mass range and try to set some limits. So let me stop there, and happy to take questions.
Great, thank you very much, Yoni. Yeah, let's have some questions. I'll let other people go first before I launch into mine. Does anyone from the audience want to go? Yeah, Will. I think you were first.
Hey, can you hear me okay?
Yeah.
All right, sweet. Awesome talk. Thanks, heaps. You said that 1,000 seconds for this kind of domain or precession is like reasonable, but hasn't been done before.
Yeah.
Do you have any numbers on these experiments from the 90s or whatever most recent experiment?
So
what number they actually got to, and what's your kind of experimental limitations to push it to 1,000 seconds?
Yeah, I mean, so as far as I know, so this was brought to my attention by, again, my collaborator at Northwestern, who's like, hey, there's this funny phase that people looked at in the 90s. What can we do with it? I don't think he set this particular phase up in his laboratory recently, but you could just read off from this plot that this thing decays on a timescale of like, I don't know, 0.2 or 0.3 seconds. So again, this wasn't trying to do anything to optimize it. So really the question is, where is T1 coming from? It's coming from at least two sources, which is surface losses and volume losses. So surface losses, you can play games using the fact that helium-3 and helium-4 don't like to coexist. So if you coat your walls with helium-4, you can actually keep more of the angular momentum in the system. The volume losses are a little bit trickier. You can try to estimate those from microphysics. I haven't done a deep dive into that, but I would say probably getting 1 second coherence times, once you can get this phase set up is pretty reasonable. I'm not sure what it would take to push that to 10 seconds, but that's what one of my collaborators has applied for funding to do exactly that.
Cool, thanks.
Anyone else?
It might be just something I've misunderstood, but I think on slide 19, you said that you could scan over 10 to the 4 axion masses. What do you mean by 10 to the 4 masses? Do you mean 4 orders of magnitude?
So what I mean is that each axion mass really is, MA to MA plus 10 minus 6 MA.
Right.
Right. That's the frequency bandwidth of the axion field. And if you, 10 to the 4 masses means basically 10 to the 4 steps in frequency space.
Right. Okay. Thanks.
10 to the 4 independent, statistically independent axion masses you could be looking for.
Yep.
Yeah.
Cool. Thanks.
All right, maybe I can go. So, I guess the simple thing is there no more recent data than this 90s experiment that nobody has bothered setting one of these things up that you could look for an axion signal in?
So as far as I understand, there's some funny sociology with helium-3. It's that it was super, super popular in like the 80s and the 90s, and then it was just considered solved and boring. And so to my understanding, there's only like 4 or 5 labs in the entire continent of North America that can do helium-3 experiments. So one of them's up at Northwestern. One of them is John Davis's lab at University of Alberta. He was actually a graduate student of Bill Halperin. And again, it's not considered like sexy condensed matter research for reasons I don't fully understand. So I don't know. I could not find, the only data that I could find on this comes from just the same set of experiments that are reviewed by these two authors, Bunkov and Volovic, and these various archive papers and proceedings and stuff. So I don't know. It'd be great if there was, but I don't think it's anything like the co-magnetometer data for this particular phase, unfortunately.
Will, do you have a comment on that?
Yeah, I have a kind of another follow-up question. So what's the system that gets this down to a millikelvin? Because that's That's pretty insane, right?
Right. I think
that's
it's
no easy
adiabatic.
feat in itself.
Yeah, I think it's adiabatic demagnetization, which is condensed matter physics for magic. So I mean,
Right.
yeah, like you have to have very, very, very specialized equipment to get down to these temperatures, and it's kind of like the only reason you would have such equipment is to study helium-3. Again, to my very naive understanding.
Yeah. And again, and this hasn't. I'm sure if this hasn't been done since the 90s, there's probably various other ways to improve this system in terms of volume and I don't know, et cetera,
Well,
et cetera.
so volume, you're kind of limited by just the availability of helium-3 in the world. You can get more of it from tritium decay. Unfortunately, that is, highly regimented or highly controlled for obvious reasons. Like the cost per liter is such that 1,000 cc's is already pushing the multi-million-dollar level. So again, my colleagues tell you that 10 cc's is reasonable for a 1 PI lab, 100 cc's is kind of pushing it, and 1,000 is like, if you found the axion in a photon experiment and you wanted to confirm it, then maybe you could get the money.
Maybe I can have some more technical points. So this in the case of CASPEr, you made this distinction between T2 and T2 star, just like the theoretical one and the one they actually have. I think in your third point of your conclusions, you're sort of arguing that this is not an issue here because
that's right. There is no such thing as T2 in the system. Yeah, there's just whoops, sorry. There's just T1.
So there's no T1 star, like a sort of the real one that they would observe.
No, there's not. Yeah. Sorry, this share keeps going away. And again, that's just it's just a function of the fact that this system locks together the transverse and longitudinal magnetization. So there's only one relaxation time in the system, and it's sort of by construction insensitive to the variation in the B field.
But I guess, is it still possible to have inhomogeneities in the B field gradient? Like, isn't the gradient because you've assumed it's just this linearly decreasing thing? Could it be something which doesn't exactly linearly decrease and has some?
Yes. So the assumption of linear gradients is not necessary for the phenomenology. So one thing you can ask is what happens if the B field is not monotonic? If it goes down, then it goes up. Then you just get multiple domains.
Right, okay.
And so it just becomes more kind of the analysis becomes a little bit more complicated. But really what's going on is so what is the domain wall? It's not some like hard thing. It's like you have a soliton type kink where you're going from zero tip angle to the magic tip angle, and you continuously pass through it. And the domain wall is just sort of what you define as the middle of that, Tanch curve. Now you can just imagine, you just like multiple solitons, you can have like, an anti-soliton and a soliton, you can get sort of multiple domains that'll all be doing their own things. The dynamics of which are all governed by the local B field. So it doesn't mess up the system at all. It just kind of, I think it just complicates the analysis.
And is that the same also if you have like inhomogeneities in like the transverse direction where like the domain wall might not be exactly perpendicular? You have like some shape to it.
Yep, exactly.
Yeah, cool. I also want to just digest a little bit more your constraints. So this sort of like structure where you have these like teeth, is that so each one of those kind of teeth is like one scan of the domain wall from top to bottom, and then you're just you're getting down in coupling just by doing that over and over again? Is that
exactly? Yeah.
And the black one is when it's sort of your gradient is only for one coherence time, is that right? Or is it just
it's actually much less, right?
Oh,
so alpha z naught should be 0.02 to be one coherence time, and here you've tuned it to be really small, so you sit in a narrow frequency range, but you can measure there for a long time.
Yeah, okay, I see. The x-axis is quite it's quite, is it actually, that's a point. So like you mentioned there's a maximum B field that you can use. Is there a minimum B field that you can use? Why can't you go lower?
No, it's just that the signal to noise goes like goes like MA. So it just you just lose a little bit by going to lower masses. So we kind of pick the mass range where you get the closest to the QCD axion line.
Yeah, I think you may have referred to this when you were talking about including this daily modulation, but like the direction of the axion wind will also not just vary because of the daily modulation, but it would also vary from coherence time to coherence time, right? Because
that's right.
Well, you're drawing a random velocity effect with each time.
Yeah, exactly.
Something you're including also in your.
No, so none of that is included here. This is assuming a perfectly, transverse and fixed direction axion field. And so the question is, how much can you buy from the daily modulation? If you're only measuring in one coherence time, kind of none of that really matters. But roughly what you'd expect is you're probably going to get some cosine squared theta penalty from the random variation, because you only get a resonant signal if it's in the transverse direction. Longitudinal axion fields imprint very, very fast oscillations on the phase that average to 0.
Yeah. And maybe a sort of small question. So this coupling is really strictly it's the neutron coupling, right? Not a sort of just the generic nucleon coupling, or primarily coupling to this unpaired neutron in helium, presumably. Is that right?
Yeah, I mean, I've lied a little bit. It's really the nucleon. It's the effective field theory of it's the nucleon. The nucleus coupling. This is like the overall coupling of the helium-3 nucleus.
Okay.
Which is some over the the proton and neutron couplings. And so I might have fibbed a little bit in translating the neutron star cooling bound onto that plane, but up to order 1 factors, that's probably okay. Yeah.
Because there's this, because with the QCD axion, there's like the DFSC neutron coupling. It the uncertainty allows for that to be 0, which is why it sort of is this whole corner rather than just a line.
Right, but you can still live off the coupling of the proton spin. Yeah.
That's sort of what I was asking. Yeah. Okay, cool.
Yeah.
All right. Anyone else want to jump in before we close off? Okay. Well, I'll